All right, concentration changes over time. So, luckily, you don't need to know how these equations are derived because it involves calculus, but essentially you need to figure out what formula you're going to use and then apply it. So on our constant equation sheet, we have these in kinetics. As a reminder, kinetics is just the study of rate of reaction. And so these three equations on the top are known as the integrated rate laws. We'll deal with the bottom one later. And you need to know which one corresponds to which. So the first integrated rate law is for a zeroth reaction order reaction, and then the first and then the second. So again, make sure you know that is the order. You can see that K is still the rate constant, and then you have your concentrations of stuff. So make sure you know which one is which. Okay, so I have it off to the side over there. And so the subscripts, in case you're still confused about the subscripts, the T is whatever time frame you're trying to analyze, whether it's 5 seconds, 100 seconds, 20 years, whatever. And then the 0 corresponds to initial, like it always does. And so remember line graphs, right? Y equals mx plus b. You have m being your slope and then b being the y-intercept and stuff. And so these kinetic rate laws are actually written like a line. And so you can reorganize it, the original y equals mx plus b. And then if you notice, that arrangement looks exactly like the kinetics rate laws. So make sure you remember that all these could potentially be line graphs. And so when I line them up, you have the 0th order. So you can see here that the first one corresponds to y, b, and then mx. So it's just taking what is in the constant equation sheet and applying it to y minus b equals mx, and it's just showing it right there. Same goes for the first order. So here we could see again, it's following that same pattern, and second order follows that too. So again, all of these could potentially be line graphs. Oh, I'm blocking it. My bad. And so remember, again, they can be line graphs. I'm going to show when they do. Okay, so you need to know about the graphs. I haven't shown the graph yet, but you do need to know them for potential FRQs. And you can either remember that it makes y minus b equals mx, or you can memorize it however you want to do it. I personally remember it as rearranging the generic slope equation thing and then figuring out which one is which. So for the 0th order reaction, your graph is going to be linear when you're looking at the concentration of A versus time. And that makes sense because if you're looking here, you have this and then you have time. Wow. And so your slope is negative k, as you can see right here, because that corresponds to the m. And so if you have a 0th order reaction, that graph is going to be linear with that slope. And then I could talk about the other ones as well. So the first order, we're talking about natural log being the y, and then you have time, and that is linear. And then your slope is negative k, just like it's, shown here. And then I could say the same thing for the second order, where I have the y being 1 divided by concentration of A, and then in this case, the slope is k, not negative k. So you just keep that in mind. Now, you're like, we haven't even seen a graph yet. Well, here's your graphs. So you have the 3 different graphs. So you have the concentration of A versus time, natural log of A, and 1 divided by A. And so looking at these graphs, you could determine what order it is just based off which one makes a straight line. And so if you notice, the third one makes a straight line. Since that third one is making the straight line, going back here, you find the one that it corresponds to. Since it was 1 divided by A versus time, that means this particular reaction is a second order reaction because that's the one that was straight. So again, 1 divided by A versus time, that is the straight line, k slope. And here, 1 divided by A is your y, and so k is your slope, and so that's why it's a second order reaction. So automatically, you look at the graphs, which one's a straight line, and then looking at the integrated rate laws, determine if it's the 0, the first, or the second order. So you could do that now. And so here are the three, again, different graphs. And so again, it is the third one because it made a straight line, and that corresponds to second order. So now we can answer the questions that were part of the problem. I just wanted to talk about the graphs to emphasize how to use the graphs and determine whether it's 0 first, second. So for the first one, what is the rate law of reaction? Represent a rate constant Sk, not numerical value, so that's nice. You don't have to solve for K. And so what you need to do, well, again, it's second order based off what I said. And so we can write the rate equals K A to the second. Now, if you look, the reaction was just A to make B. And so since I only have one reactant, I can automatically just put the 2 as a superscript because it was a second order reaction. If there were multiple reactants in this problem, I wouldn't necessarily know which one is which. So for example, if it was like A plus Z plus Y makes B or whatever, I wouldn't know which one, would have which superscript. For example, one of those reactants could have had a 2 and the rest have zeros, or 2 of them have 1s and the third one has 0 or whatever. But since this is just A to make B, then I could just put a 2 there because I know it's second order. So that's how you answer that first one. Okay, there are 2 points for this question because this is an older FRQ before the new standards. So one is just giving the answer, which is the rate equals blah, blah, blah. And then the explanation of why you chose that. So, talking about which graph made sense. It's the second order and then representing that. Cool. And so we could estimate K, and you need to show your work. As a reminder, K is just slope, so slope is the change of Y over the change of X, so you just have to put, 2 data points on that linear graph, and then you can estimate K. So it's just slope. So I picked 2 random points, and so you can see them here, so 0, 5, and 225, and then you just plug it into your slope. You put change of Y over change of X, do the math, and I get 0.1. Don't forget your units if it has units. So in this particular case, this has units because I know which graph it is, and so I could just plug in my units, again doing the math, and then you're good. So there we go. You get 2 points. So 2 points is setting up the slope equation. Again, it's change of Y over change of X. I didn't show that on the screen, but I assume you know how to do that. So change of Y divided by change of X. And then you have your answer with your units because your units are in the graph. So you should show your units for that. Cool. We know some information, so now we can solve for the third one. And so you have an initial concentration, we have some time, and so we could just literally plug and chug. So we know it's a second order, so you want to make sure you use the second order integrated rate law. So here's the constant equation sheet. Again, it goes in order, 0 first, second, and so the last equation corresponds to second order. This is the information I know in terms of givens. You have the K value that was calculated in the previous question. You have the initial concentration, so I wrote that down as A with the little initial symbol equals the concentration of 0.2, and then 30 seconds. If you get lost, organize your stuff based off the guess method, okay? So that's why I did the givens, okay? And so we plug and chug into that third equation, so literally you just do that. So I plug in this value down here, and then I have my K value is 0.1, and then my T is 30 seconds. So I'm going to go ahead and plug in the values just to show the algebra, but honestly, I assume you know how to do algebra, but just in case. So we have the variable here that needs to be by itself. I'm going to go ahead and add this term to both sides. So 1 divided by AO equals 0.1 times 30 plus 1 divided by 0.2. And then you want to do reciprocal stuff, so you can inverse everything. So that equals 1 divided by whatever this answer is on a calculator, you put it down there. And then 1 divided by that answer gives you your answer for initial concentration. So you would get 2 points for that. You would get the points for the setup, so like setting up, and then the actual answer. In this case, once you do this math, the answer is going to be 0.125 molar. So make sure that you have done the algebra correctly. I didn't do sig figs. It's 30 seconds, so it's 2 sig figs. Oh, that's annoying. Or 1 sig fig, I mean. That's really annoying. Oh well, it is what it is. All right, so here's your turn. So there's 4 questions and some graphs. So see if you can do it. So pause the video first before I start talking about the answer. All right, ready for the answers? Here we go. So first, it's writing the balanced equation. I don't know what else to say, so there's your balanced equation. And then you determine the order. So looking at the different graphs, we have the concentration over time versus natural log in time versus 1 divided by concentration over time. And which one made the straight line? It's the first one. And the first one corresponds to first order because, as a reminder, look at these. This is the 0th, this is the first, this is the second, and so this one would have been the 0th order right here, because this corresponds to this. Then this guy here corresponds to the first order, because you have the natural log part here, you have the natural log part here, and then this corresponds to the second order, this part corresponds to this part. So since this was the straight line, this is my answer, first order. So, since we know it's first order, we can write down the rate law. And so the rate law is rate equals K, and then you put the reactants, and then you put exponents. Now notice there's only one reactant, and it's a first order reaction. And so since it's a first order reaction, I can just put to the power of 1. And when you have the power of 1, it's just itself, so you are just good with that equation. That's it. And then you can estimate the rate constant, the K value, and so you just do change of Y over change of X. I picked 2 random points and estimated it. Your numbers might be slightly different than mine because it just depends on how well you estimated based off this graph. Usually the College Board graphs are easier to read and it wouldn't require as much estimating, but since I gave you this one, you just estimate whatever points you decide. And then you calculate, and then you're good. Natural log, just as a reminder in case you forgot from algebra, is unitless, or it doesn't have dimensions. So if you were to look at the calculator and look at the graphs based off, the one with natural log in it, it doesn't have units, so it doesn't have a molarity. And so if you want to know why, you can look at these links on the class slides if you'd like, but you don't need to know, so who cares? But if you're curious, you can look. All right, half-life. So half-life was covered in Gen Chem, but if you forgot, half-life means half the concentration of its initial value. But what does that actually mean? So naturally, things decay over time. And so you have a time limit where half of the original substance decays into something else. And so usually we call this parent versus daughter. So you have an original substance, aka the parent, and if I had 100% of it at, initial start of having it, if the half-life happens, so for example, if the half-life was like 5 years, so that means 5 years has happened, then that means 50% of it decays into daughter substance, whatever substance it's making, and then 50% remains as parent. So that's what half-life means, where half of it is changing into a different substance, aka the daughter substance. So the most important half-life to know is first order. It's the one where the half-life is constant. It's easy to calculate. If you're doing the other types of rate law stuff with the other orders, it's way more complicated. So we're just focusing on the first order for this class. And so it relates to the rate constant. You can literally see it on our constant equation sheet right here. And so t half equals that number divided by k. And again, k is just the rate constant as you remember. And then t half is, well, half-life, as you can see right here, where it's referencing what it is. And so make sure that you can find the equation, and it's literally just straight up plugging and chugging. There is something else to know just in case, though. So there is an equation that you need to know so you don't have to like continually go over for a million half-lives how much you have left. Now obviously the math is easy, right? So if one half-life happens, you have 50% of the parent, you have 50% of the daughter. In two half-lives, as you can see here, you have 25% of the parent, and then you have 75% of the daughter substance. And then 3, 4, 5, 6, 7, however many half-lives happen. Now, it's easy to just divide by 2 every single time, or you can memorize this equation here. So I recommend memorizing the equation so you don't have to half a million times. And also, the other thing to know is you don't need to be 100%. You can start off with the initial concentration, which is, just whatever initial concentration you have. If you're starting with like 5 molar of a substance, then you could put 5 molar on top divided by 2n, and then however many half-lives have passed. And so the example I'm going to actually use the concentration one. So as I've mentioned, you don't need to know the other orders' half-life stuff. You only need to know for first order. You need to know the equation is for first order, so just make sure to know that in general. Okay, so this is radioactive decay. So if you've heard about the elements that can't exist very fast, like the later parts of the PT where you see the atomic masses in parentheses, those are radioactive and they don't last very long, and so they decay. Other stuff decays too, but it just depends on time and such. If you want to learn more about radioactive decay, definitely the other chem classes will talk about it more, but we're just touching it a dash, just a little bit. Okay, and so here is an example problem, so read it to yourself before I start talking about it. Okay, ready? Okay, here we go. So you literally are just using the equation from the constant equation sheet. So you'd have the t half equals 0.693 divided by k. The k value was given because it literally is right here. Rate constant is that. So just again, taking that equation, putting in k, you got your value. The end. So very easy stuff, very easy stuff. Now it says how much do you have after 5 half-lives? Take the equation from the last slide, except instead of 100%, you put the initial concentration, whatever originally you had. And so originally we had 0.053 molar of that substance here. And so then you do 2 to the 5, so you have 5 half-lives, and then that's how much is left of the parent, aka this thing. So that is how you calculate. Not too shabby, not too shabby. Now, one thing this question is not asking about, but could have asked about, is how much time has passed after, this many half-lives. And so if I know the half-life time, so this one right here, and I did 5 half-lives, well, you literally just multiply it. 5 half-lives times this is that many minutes have passed for 5 half-lives to happen. Cool. Now, the other way, if you did want to use the 100% equation instead of the original, doing it like this, so I could use the percent. I can calculate the percent that is left, and then I take the original concentration and then I multiply it by the percent, and then you could see it's just 0.0017 molar remaining. So here is your turn. So there's a problem and then it has multiple questions, so go ahead and pause the video and try it yourself. Ready for the answers? Here we go. So we have the first one where we're just calculating the half-life. So again, literally take the equation from the constant equation sheet and then plug in the K value given, the rate constant. And so there we go, we got seconds. Now, it didn't say you needed to change the time, but whatever units you decide to use, you decided to use. It ends up being 5 days, but again, it doesn't matter. It doesn't say specifically what time, so pick a time. You could stick to seconds if you'd like. It doesn't matter. And I changed it to days mainly because I just want a smaller number. I don't like 10 to the 5th. It's too big, too big. Anyway, so for number 2, we have the original flask containing 0.077 molar of this substance. And so after 4 half-lives, how many of that substance do you have left? And so you literally plug it into the equation I said you should memorize, and then you have that. You can also use the other equation where you have the 100%, calculate the percent, and then multiply it by the original substance. Either way is fine. And then you have the last question where it says here you're going through 4 half-lives, and so you just take the 4 half-lives, you take the time that each half-life is, which is why you could see here I just cancel out half-life, and then you have the days, and then you have 20 days. Or if you did hours, then I have the calculation for hours, or if you have seconds, I also have the calculation for seconds. So again, whatever units you decided to use, just stick to it. You don't have to reduce the number down if, you see something hecka big, unless the problem tells you. That's why I say whatever units you use. And honestly, that's it. So there's not too much to know. You just need to know the graphs, and then you need to know the half-life equation, and then you need to know the other half-life equation that isn't on your constant equation sheet, the one I showed with the examples of the 1 half-life, 2 half-life, 3 half-life thing, the one I used for question 2 on this Your Turn, and that's pretty much it. Okay, bye!